as to what are pipe climbers, what are the types of pipe climbers, um, what is the relevance of pipe climbers or pipe climbing robots today, what are its applications, uh, and what are the issues involved in pipe climbers. One of the issues, of course, is the development of grippers. So, in the next part, I'll be explaining a little bit about grippers, specifically with respect to pipe climbers. And I'll be focusing in particular on what are known as inchworm climbers or inchworm climbing robots. And finally, I'll present a little bit about the work which I have done here at IIT Guwahati. We have developed um, a gripper here using compliant mechanisms at IIT Guwahati here, and I'll just present a little bit of detail on that. So I'll draw a little bit about my own work in this presentation. So firstly, I'll just give an overview of what are pipe climbers. Now, pipe climbing robots are basically autonomous robots which navigate the exterior or interior or pipes, and primarily they are used for inspection, monitoring, maintenance, or repair. So just to give you an idea of what pipe climbers are, uh, I'll just share a video which was developed of a pipe climbing robot which was developed by the Hosei University in Japan at the Intelligent Robotics Laboratory. So here you can see this pipe climber. This is basically a robot that is navigating across a structure that resembles a pipe. So this is what we are referring to when we talk of pipe climbing robots. Of course, over here they have used um, a particular kind of locomotion method, which is very similar to how humans use uh, to climb a pipe or to climb, for example, any circular structure. So, for example, if you can just picture how a human would climb a tree, right? This motion resembles something similar to that. So, this is one kind of locomotion method, one kind of way of climbing, of making a robot which can climb a pipe. There are, of course, other ways also, as I'll just explain. But before that, uh, I'll just introduce you briefly to the types of pipe climbers. Now, the types, of course, depend on how you want to classify them. The first way of classifying is external versus internal pipe climbers. So, internal climbers are those robots which navigate the interior of pipes. So, for example, this is a robot built by the Mechanical and Aerospace Engineering Department at Singapore Polytechnic. So you can see it is navigating within the pipe, whereas this one here, built at the uh, KERI Robot Lab, is navigating on the exterior of pipes. Right? So this, of course, can navigate not only along straight regions, but also along curvatures, bent pipes, and so on. Now, this is one way of classifying. Of course, another way of classifying pipe climbing robots is by the type of locomotion. Now, I've already shown you an example of a legged robot, but you can also have what is known as a wheeled robot. For example, here is a wheeled climber developed by the University of Tehran. So here you can see that the robot is powered by some kind of wheel structure, and this wheel is enabling it to move over the pipe. And legged climbers, of course, I've shown you one video. Here is another video of a legged climber navigating a bent pipe. This is using um, uh, a leg type of structure instead of a wheel to navigate, to hold onto the pipe and to climb the pipe. So this is another way of classifying. Now, before I proceed further into a further description of what are pipe climbing robots, the first question which should be asked is, of course, why use any of these pipe climbing robots, or what are its applications? Now, these robots, pipe climbers, they are part of a larger and emerging area in robotics, which deals with the development of pipe inspection and repair. Now, this idea of inspecting and repairing pipes, it has importance, especially, for instance, in the oil industry and in nuclear petrochemical industries. Now, as I'll explain in this presentation, the existing solutions for inspection and repair, right, they are quite costly and in some cases very, very inefficient. And this is assuming that these pipelines, for instance, can even be inspected at all. So just to take an example, a recent survey was done in which the UK, for instance, has about 200 miles of high pressure pipelines, which can't be monitored with the current technologies. So these pipe climbers have some kind of application in this particular area of pipeline inspection and repair. Now, the question is, why is inspection and repair important? Again, if you think about it trivially, let us say that you have an oil pipe burst. Apart from loss of revenue, of course, you can get some kind of environmental disaster also. Two famous examples, I'm sure many of you might be aware of this. Uh, the Exxon oil spill, which happened in 1989, which spilled many million gallons of crude oil, uh, led to an environmental disaster. Many of the seabirds, otters, seas, whales, they were killed because of this. And this oil slick, it covered about 1,300 miles of the coastline. So this was one example. And the second example, which is actually even worse than the first, is the Deepwater Horizon oil spill, which happened when you had a drilling rig in the Gulf of Mexico and it exploded. And it resulted in the death of 11 workers. And you had 4 million barrels of oil which flowed out and which damaged this Macondo well over an 87-day period. So these are just small examples of why inspection and repair of pipelines is important. Now, what are the problems with the current technologies available for pipeline inspection and repair? Now, pipes, as we all know, they are vulnerable. They are quite susceptible to corrosion, cracking, and other defects. So it's very important to discover these flaws in pipelines at an early stage before the defect becomes a big one. The second thing is that um, if they do not discover it, if these defects are not discovered, then of course the operators have to go for repair of the pipeline. And in many cases, the operator has to shut down the pipeline. So when you shut down a pipeline, of course, this again results in loss of revenue. The current methods, the ways of inspecting pipes, they are broadly classified into two types. One is the internal way, where you have what is known as an intelligent pig. It is sent into the pipeline and it is carried along by the pressure differences in the fluid. Now, this of course has an advantage that um, the pig enters the pipeline without stopping operations. But of course, it also has drawbacks. For instance, um, it requires a lot of preparation and it isn't suitable for depressurized pipes. The second way of inspecting pipes is, of course, the external way, where you send a group of workers and they visually check the pipes for any signs of leakage. But this is, of course, very inefficient. I mean, you have many, many miles of pipelines. So if you want to visually check the pipes, you can imagine how inefficient it is. And of course, it is expensive because you need a lot of manpower for this, and it is also dangerous, especially when you're dealing with the oil and nuclear industries. Also, this visual inspection, it doesn't give much of information uh, for what are the defects, whether the defects are fully materialized or not. As I mentioned earlier, you have to be able to identify a defect before it becomes a big defect, before it becomes a problem. And visual inspection is a bad way of doing this. So this is actually helpful, in at best the worst cases of leakage, where you have obvious cases of leakage. There, of course, visual inspection works, but it doesn't give you much of information when you want to identify defects beforehand and you want to address them beforehand. So these are the current ways of inspecting pipes and the problems with them. Now, there is an additional challenge, of course, when you are inspecting subsea pipelines. So here, for instance, the operator has to mount uh, a production storage and offloading unit on the site of repair, and he has to send down some divers to cut out the damaged section of the pipe. Now, this idea of doing repair from the inside, it hasn't been taken seriously until very recently. And furthermore, condition monitoring of these pipelines is one of the most critical challenges, and it is one of the most uh, it is one of the areas which is increasingly becoming important today. What do you mean by condition monitoring? Of course, you monitor continuously the condition of these pipelines. Uh, you do it continuously. It is not just that once you are going and doing some kind of visual inspection, you do a continuous monitoring of these pipelines at every stage. So from this, basically, uh, due to these challenges which are there and due to these problems with this pipeline inspection and repair, increasingly people are turning to robotic inspection and repair technologies. In particular, those with machine learning and AI enabled technologies. So this is actually a huge industry. Um, it is an upcoming industry, and it is perhaps one of the industries which, um, given the amount of funds that we all know the oil industry and nuclear industry has, this is perhaps one of the more important topics uh, in the area of robotics in the future. Just to give a brief idea of the current and upcoming inspection and repair technologies, uh, you have X Robotics XR1. This is the name of the robot and the company, X Robotics. So this robot was designed for inspecting equipment and facilities in chemical processing plants. It is equipped with a wide range of sensors and cameras along with wireless communications so that um, people can control this robot from a remote location. Uh, this is important given that, as I mentioned before, in oil and nuclear power plants, there is a physical danger involved when you manually go and inspect the pipe. So it is important to have some kind of remote control over robots. The second robot which I'm showing here is one developed by the company Shell. It is the name of the robot is SensorBot. It can carry out inspections of oil and gas field equipment in many challenging environments. It is also controlled remotely by operators. This is important. And additionally, it can also drive through gravel, mud, snow. It can climb vertical surfaces using rails and so on. Um, Another one is known as FSW bot. It is currently being developed by Fourth Engineering Enterprises. It is able to conduct repairs on subsea pipelines, eliminating the need for divers or lengthy breaks in operation. So this challenge with subsea pipelines, which I mentioned, as I mentioned, manual repair, you need many divers to actually go in and check for problems and conduct repairs. So whenever you have um, a problem in a subsea pipeline, you have to hire divers and you have to ask them to go down and check and inspect. Now, if you see the rate, and this is something which we actually did, um, I did a survey, me and one of my colleagues at IIT Guwahati, we did a survey for how much each of these divers would charge. And they charge, uh, perhaps in some cases, depending on the problem, in lakhs, um, in some cases for a day, in some cases for an hour, depending on the type of problem. So this is a very, very expensive thing. Um, Also because there are not many skilled divers, the demand actually is more, and that is what raises the cost even more. So by having this kind of robot, you're actually eliminating, at least partially, if not completely, the need for divers, and also breaks in operation. As I mentioned before, whenever pipelines need to be repaired, very often they have to be shut down. So when you have a robot which is inspecting, then of course there will be significant uh, advantages in that you don't need to have any breaks in operation, right? So in this case, this device, it will go into the pipeline at the point of entry, and then the oil which is there in the pipeline will carry the robot to its required destination. Then it will detect that repair patch, and then it will deploy the patch in one of the systems. So the benefit here is that the operator doesn't actually have to close down the pipeline. That is one advantage. So those were just some examples of some robots um, which have are increasingly becoming being built by industries to inspect and repair pipelines. And this area of inspection and repair, as I mentioned, is an upcoming area in the area of robotics, and it is likely to become a very huge area given the amount of resources, amount of finances which are involved. Typically, oil companies, petrochemical companies, nuclear related industries, the finances involved are huge. Um, so any if they have to shut down plants to do inspections and repair, it's going to cost them very much. So that is why a lot of them now are investing in this kind of inspection and repair technologies, in the development of inspection and repair robots, so that they have to avoid shutting down the pipelines for inspection and repair. So I'll briefly go through the applications of these pipe climbing robots. So this is just a brief summary. Uh, Pipe climbing robots, they can be used for inspection of industrial pipelines. Uh, they can explore locations which are not accessible to humans. For example, the interior of pipes especially when you have pipe bends, when you have pipes of changing diameters. These may not be accessible to humans, and that is where robots can play a very large role. They have higher reliability and intelligence. They can avoid the hazards um, associated with these industrial pipes, especially in the oil and nuclear industries. They can navigate through complex geometry, like I mentioned, pipe bends, pipes of varying diameters, in some cases, even broken pipes. Um, the One of the major function of these pipe climbers is to detect leakages, to inspect wind turbines. This, of course, in wind turbines. Also, it involves pipe climbing. Of course, when you want to reach the top of the turbine, of course, you have to climb that pole which is there. And finally, measurement of wall thickness. This also is a function of pipe climbers. The second major application of pipelines is in the field of vertical structures. Um, the basic role that these pipe climbing robots play is that they are autonomous systems, so they reduce human involvement. That is what increases their efficiency, safety, and so on. And they have high repeatability. And finally, this was for inspection, and of late, there are robots being developed even for repair. For example, this robot which I just showed, FSW bot, it can also do repair. So inspection is one part, and of course, repair itself is another part. So repair involves the welding of ship hulls, the sealing of cracks, and general pipeline repair. If you want to put a clamp on a pipe, for example, increasingly there are robots which are being explored to do even these kind of things. Now, moving forward, what are the issues in these pipe climbers? Uh, these are important from a technical point of view. For example, the locomotion. You need to think, should the robot have arms and legs, or should it have wheels, or should it have sliding frames or wires and rails and so on? Now, earlier I showed you some legged robots and I showed some wheeled robots also. So each one has its own advantage. The if I can just go back. So this was the example of legged climbers. This was the example of wheeled climbers, and this one for legged climbers, right? So each one has its own advantages. This one is a bit slower. This one is perhaps relatively faster, right? But this one could be more stable than this one. So there are a variety of advantages and disadvantages. So this locomotion is one of the issues that you have to consider when you are developing pipe climbers. A related topic related to locomotion is gripping. Now, gripping, of course, you can have um, magnetic gripping, pneumatic gripping, mechanical, electrostatic, and chemical. I'll discuss gripping in a little bit more detail um, in this talk a while later on. But this gripping is actually dependent on the locomotion. So they go hand in hand. The third is mapping and navigation. That is, the robot must be able to map the environment. Now, what is the meaning of mapping the environment? It basically means that when the robot is moving across the pipelines, you have a pipeline is a pipeline system is it runs into many miles. So a map is basically needed to for the robot to create an image of where things are in a given location. So just to give you an idea of what a map is, um, when you talk of mapping, you're basically talking of creating a mental picture of how the entire surroundings looks like. So the robot must be able to map the environment. It must be able to detect obstacles in its path and avoid them. And it has to navigate over slimy surfaces. So this is another challenge in this area. The next is manipulation. If you have climbing robots with high manipulability, then that is desirable. However, you also would like a certain amount of rigidity. It should not be completely flexible. And in design of robots, uh, there are about 4 or 5 factors which are extremely important. Uh, One is the velocity and mobility. It should have, it should be able to travel relatively fast. It should be able to carry a high payload. For example, if you want to repair, if you want to conduct repair, if the robot has to autonomously conduct repair, then of course it has to carry the repair equipment with it. So it has to be able to carry a high payload. That is something that is desirable in the design of these robots. The last two are related to safety and reliability and usability. So depending on different kind of surfaces, you have to see which kind of robot can be used and which one is more reliable and safe for a given environment as compared to others. So these are some of the issues in pipe climbing robots. These are technical issues which have to be addressed. Now, my talk will largely be on grippers. This is what will be the main focus of my talk. Uh, so I'll just explain the importance of gripping. What do you mean by gripping? If I had to define it technically, then it is basically the need to create a sufficient adhesion force between the surface of between the surface and the body of the climber. So here, when you see this robot which is climbing, it is basically creating some kind of adhesion force between this surface and this body of this climber. So the common way it is done is to press. The robot tends to press against the walls of the pipe so as to generate sufficient friction force, right? And higher the gripping force, of course, higher the normal reaction and higher the friction force. Now for gripping, if you want to get the desired gripping force, the grippers have to be actuated and pushed against the walls of the pipe. So this, for example, here you have to be able to have an actuation mechanism that is able to push against the walls of this pipe. So that is typically how gripping is done. The types of grippers, which earlier I had described, you can have magnetic adhesion, pneumatic, electric, mechanical, strain energy, chemical, and self weight. There are many types involved here. I'll just describe some of them. I'll start with magnetic adhesion. So here you basically use electromagnets as well as permanent magnets, which are positioned on the surface, right? Or they are kept at a certain distance away from that surface that on which that robot has to navigate. Now this principle, of course, it is using the principle of magnetism. It is very reliable on ferromagnetic surfaces, and you can create very strong adhesion forces in a very small area. And if you use rare earth magnets, then of course you can create adhesion without energy consumption. Some common applications of these are in inspections, maintenance, and construction works of steel tanks, ship hulls, and high power poles. Now, how do you describe this adhesion force? I won't get into too much of technical details here, but the, uh, the strength of a simple pole magnet, for instance, is often given as the pull force. Fp equals b square a by 2 mu naught. This is Maxwell equation. And this is the pull force, and the force exerted on the material, of course, is given by this expression. I won't get into details of this, but this adhesion force, for instance, what we can say is that it depends on the internal structure, the ferromagnetic characteristics of that surface, and primarily the distance between the magnet and the surface. So this is magnetic adhesion. One example of this, for instance, there was a multi-terrain robot which was built for petrochemical applications. This was published in Breza et al. 2012, right? Where you had a ferromagnetic surface and you had magnetic pads installed on this robot, uh, which is known as WinSpec bot. This is based on using permanent magnets which are attached to these steel surfaces, and they are able to effectively create adhesion force over here to be able to grip this ferromagnetic surface. So this is one example of what magnetic adhesion looks like. But of course, as I mentioned, this is applicable only for ferromagnetic surfaces. Now, another type of adhesion is known as pneumatic adhesion. Right? Just to give an example, this is basically it is perhaps the most commonly used in the field of climbing robots, and it is very popular in particular for wall climbers, the development of wall climbers. So this uses a principle which is known as negative pressure principle, uh, wherein you create a negative pressure relative to the atmosphere for holding on to the surface. So this pneumatic adhesion is of many types. For instance, you can do it by having passive suction cups, active suction chambers, or by vortex systems. So this, of course, is using suction cups here, as you can see. And this particular type of climbing robot, it has applications where you don't have ferromagnetic surfaces, or where the structural points of contact are not given. So these, what happens is that the robot developers tend to apply these suction areas to increase the adhesion force, or they are able to use more light-weighted vacuum generators for producing these low pressure differences, which are responsible actually for um, uh, the providing this pneumatic adhesion force, which is able to grip the surface. So this was pneumatic adhesion. Then you have gripping with self weight. So this, of course, um, to explain this, let me explain the figure here on the left that you can see here. I hope you can see that this resembles a human who's climbing some kind of a pipe-like structure, and he has a strap around his waist. So if you see that this kind of method of climbing is commonly used by people who climb coconut trees, for example. They have a strap around their waist, and they apply pressure through their foot to maintain balance, right? So after having the strap around this waist, the foot is used to generate some kind of force and stick to the pole. And this climber, what he does is he pushes his waist back to provide more torque, right? So that way he can create more force at this contact point. So if you see how commonly you must have seen people climbing coconut trees, for example, they use this kind of method where they have a strap around their waist and they use it to generate that torque, which will be able to allow more force to be generated by the foot at the contact point here. So an example, the effect of this is basically that the person is basically able to hang on to this pole by virtue of his own weight. So, for example, when he has a strap around his waist, by virtue of his weight itself, he is able to keep himself steady by pushing himself back against this strap. So this is known as gripping with self-weight. So a robot was developed um, by a human-inspired pole climbing robot was developed based on this principle. So here, for instance, you have this as the strap, right? These are the active wheels and the passive wheels of the robot. This one is actuated. These two are not. This one is the worm gearbox, which is actuating this wheel, right? And this is the spring leg. This is the equivalent of this leg, right? And this is the safety spring that is there. So this type of robot is quite similar to this principle of a human who is actually using his own weight to create stability and automatically create sufficient force through his foot on this pipe so as to be able to climb this pipe. So the advantage of this is the more the weight of this robot, the higher is this gripping force. Because the more the weight, for example, if the person has more weight, then because of the strap, more force is going to be put on the strap, which will simultaneously mean that a greater force is available for gripping through his foot at this contact point. The fourth one is electrically actuated adhesion. So what happens here is that the gripper or the gripping device is actuated using electric power. The most commonly used electric actuators are DC motors or servo motors. So this kind of gripping mechanism is very common in what are known as snake robots. So here, for instance, on the left hand side figure, you can see a kind of snake or inchworm type of motion. This is not the robot. This is the real life living organism. And on the right hand side, you can see a model of a robot that is actually mimicking this. So here you have a robot. This is the schematic of the robot. This is a technical diagram of the robot, which is mimicking this kind of motion. So it has a few revolute pairs and prismatic pairs. Here you have revolute pairs, and here you have a prismatic pair, and here you have these grippers here and over here. So this is able to, through the revolute pairs, generate this kind of motion. As you can see here, it is able to generate this kind of motion, and it is able to push forward in the same manner that a snake or an inchworm pushes forward. So for instance, you have in the first position, you have this inchworm here, and then you have slowly the lower part coming up, and then the top portion moving upward. So this robot has a similar kind of structure which enables this kind of snake motion or inchworm motion to become possible. So this is commonly referred to as an inchworm-like climbing robot. This is the technical term. It's known as an inchworm climber. And this uses electrically actuated adhesion. Now, another robot which is based on electrical adhesion, for example, is the design of the outpipe climbing robot. Here, as you can see, you have wheels which are placed on three sides, here, here, and here. These wheels, of course, move on this pipe. And you have a linear actuator here, which is pushing the wheel on this pipe, creating a force that will actually push the wheel towards the pipe and hold it against the pipe. So that is how electrical actuation is used to uh, actually ensure that this robot is able to hold on to the pipe. This linear actuator, it provides a force in the radial direction to keep the wheel attached to the pipe. Um, Now, in the third part of my presentation, I'll be focusing on particular types of climbers, which are known as inchworm climbers, similar to what I've shown in this figure here. Now, this is a typical model of an inchworm pipe climber. As I mentioned, uh, in a pipe inchworm climber, you have two portions. The body of the inchworm climber can be divided into two portions, the lower portion and the upper portion. So first, the lower portion is pulled upward, as you can see here, and then the lower portion is fixed and the upper portion is moved upward. And again, the process is repeated. Perhaps this is not a good figure. If I can just go back here. Here, if you can see, this was the initial position, and you have the lower part being pushed upward first here with the upper portion fixed or largely fixed, and then the lower portion is held fixed and the upper portion is then pushed forward. So this is what is the basic idea behind what is known as an inchworm pipe climber. Now, in literature, if you see the various types of inchworm pipe climbers, one of the most well-read and well-known robots is from the thesis of Tavakoli M in 2010, where he developed many pole climbing robots or models of pole climbing robots. Now, these inchworm pipe climbers, of course, you can have these pipe climbing robots resembling what is known as a serial robotic structure. Now, what do you mean by a serial robot? Something which has an open chain. You have a single base here, and then you have a successive set of links which are connected through joints. So this is basically an open chain, right? And this robot is basically modeled upon this open chain kind of serial structure. So here in this robot, of course, you can see you have rack and pinion system over here on which this robot can move. And over here you have a serial chain. This is the first link, right? This is a revolute pair. This is the second link. And then finally, this is the gripper over here. So this also follows this inchworm structure in the same sequence which I mentioned. First, the lower part is closed. This is opened, right? Then this is moved up. It goes from here to here. It is moved upward. And this revolute pair actually allows it to go upward. And then this gripper is closed, it is fixed. And then this lower part is opened and this moves upward, right? So basically, this is the basic motion of a inchworm climber. That one portion, the body is divided into an upper portion and a lower portion. And the upper portion is once fixed and the lower is moved upward. Then the lower one is fixed and the upper portion is moved upward. The same for downward motion. Now, this is another inchworm climber, which has which is based on the concept of inchworm motion. So here you can see the same pattern is repeating. First, you have the lower portion fixed and the upper portion is slightly moving upward, right? Then the upper portion is fixed and the lower portion, you can see it is moving upward. So this again, it uses a largely, if you can see here, a serial chain mechanism, an open chain. You can also have inchworm pipe climbers, which are having a closed chain structures. These are commonly referred to as parallel robots. Parallel robots means it refers to robots which have a closed chain. The chain is closed. So if I go back here, a serial chain, you have an open chain, and a parallel robot, you have a closed chain. One of the most famous parallel robots, if you check out the literature, is what is known as a Stewart-Guff platform. So this was proposed by Guff in 62 and popularized by Stewart in 65. So this basically this is a 6-degree of freedom robot, right? So what you have is a platform on top, right? Or maybe this figure is a better description. You have a platform on top that you can see here, and you have a platform at the bottom that you can see here, this round platform, and you have connecting both this upper platform and lower platform, you have 6 linear actuators that you can see out here. So as these linear actuators push forward, this upper platform will tend to move, it will tend to change its orientation, right? It will tend to move upward. And then it is gripped, and then these linear actuators are retracted. They are actuated in the opposite direction. Then this lower ring or this lower platform that you can see is moved upward. So this has an additional advantage, of course, that if you can see one major difference between this one and the previous one. In this case, of course, in the serial case, you had this portion over here simply moving upward and then it being fixed and then the lower portion moving upward. The one of the advantages with this, of course, is that because of these 6 actuators, this upper portion, it can also change its orientation. It is not just moving upward, it can change its angle also. So this is especially useful if this top portion can change its angle, because then it can navigate over bent pipes by changing its angle. So you can see here this top ring is able to change its angle because of many linear actuators here, which are being positioned out here, which are connected between this lower ring and the top ring. Another inchworm pipe climber, which you can see here. It is used for construction and service applications. This also was developed by Tavakoli. Here you have same. This is this green portion upward. The green portion that you can see here. This is the top platform, and this is the bottom platform connected by 3 linear actuators. And this base is able to rotate. Here you have a rotating mechanism here at the base. So this also has the advantage that when these linear actuators press forward, this platform will be raised. So you can have linear motion. For example, the robot can climb a pole that you can see here. The second advantage is it can also rotate around the pole. How is this possible? As I mentioned, uh, similar to this concept of the Stuart platform, this top platform is able to change its orientation as well, not just its linear position upward or downward. It can change its angle also. How is this? You can see that, for instance, you have this top and bottom platform connected by linear actuators. So let us say that you actuated this part, but you didn't actuate this one and this one. So this one would move upward, whereas this one and this one would simply stay where they are. So that way, this green portion here would change its angle. So by selectively, when you select one particular actuator and you actuate only that and you don't actuate the others to the same degree, you can control the angle of this top portion here. So that is able to make it rotate around the pole that you can see. So this can rotate around the pole, this can overtake a bent section as well, and it can perform operations, welding, like a welding operation, for instance. So what are the issues with gripping? One of the challenges of climbing robots is basically the availability of proper gripping force. You need to have a good gripping force available. Otherwise, the robot will begin to slip. The existing robots, of course, they use they are able to increase the gripping force by using pneumatic cylinders or by electrical actuators. Now, a large gripping force, of course, uh, which is created by using these large pneumatic cylinders, would increase the weight of the robot also. So, which means that to make it move, of course, it would consume more energy for the working of the robot. This is another issue with gripping, right? Thirdly, the large ratio of the gripping force to the weight of the robot would also increase the payload. And ideally, you should have a gripping mechanism which should consume less energy as compared to the existing grippers. So that is another challenge involved in gripping. Um, the fourth is that, as I mentioned, one of the most important aspects of pipe climbers is that they have to be autonomous. So you have to find ways to automate this. Um, then fifthly, the gripping mechanism needs to be automated by using as many motors as the number of actuation points. Now this would of course result in an increase in the weight of the gripper, and therefore it is actually desired that this pipe climbing robot should have a mechanism that actuates all of the actuation points by using less number of motors than is currently used. And finally, we have to select a proper clamping mechanism, right? So if you see for an inchworm climber, as I mentioned, the whole idea is first the top portion, it moves upward first, then it has to clamp, and then the bottom portion moves upward. So you should have a proper clamping mechanism here. That is another issue with gripping. And clamping, of course, because you can have a variety of surfaces. Some surfaces are slippery. You require a proper control strategy for it. Um, so in this final section, um, I'll basically draw on some of the work which has been conducted in my lab here at IIT Guwahati. I'll present a gripper which we built here at IIT Guwahati using bistable compliant mechanisms. Now, this work was carried out by one of my PhD students as a part of his thesis, Mr. Saurav Kumar Datta. Uh, Now, before that, if you see the word bistable compliant mechanisms, it has two parts. One is the word bistable, and second is compliant mechanisms. I'll explain both of these words one by one. A bistable compliant mechanism is one which basically has two stable equilibrium states in its range of motion. Um, Now, this bistable compliant mechanism, it basically comprises of what is known as a bistable buckled beam. A bistable buckled beam is basically one, right, where you pre-buckle a straight column, right? You pre-buckle a straight column, and then you apply a transverse load so as to toggle it between two equilibrium states. Now, what do I mean by this? Let us say you have a straight column here, right? You pre-stress it, you pre-buckle it, right? When you pre-buckle it by the application of some force and you hold it together, after that, when you apply a transverse load, right? So then this moves to another state, as you can see here, state 3. Now here, when you apply a transverse load, F, you can see here that this moves to an unstable state and it moves to another stable state. So this bistable buckled beam, it operates in such a way that it is able to shift between two stable equilibrium states. This is one equilibrium state which is stable, this is the unstable state, and this is another stable state, right? So this is commonly referred to as snap-through buckling. I'll take some examples of this just to explain this process of snap-through buckling, just to explain what I mean, right? So this is one stable state, right? So you're pressing it here and it is staying in that state when you release the force, right? And then when you push it back, that is another stable state. Now, when you release it, it stays there. So this basically has applications in developing switches. You have two stable states, as you can see here, and by the application of force, it moves from one stable state to another stable state. So this is known as a bistable system. Just I'll show many examples of this. right? This is a bistable joint, right? This is a stable state. Another one here, this is one state, this is the second state. This is one state, it is the second state. Here, when you see you increase the voltage, it reaches one state. Then when the voltage is decreased, that is the force being applied is varied, it changes to another state. This is another example. This is a bistable needle, right? So this is what we mean by bistable mechanisms. Right? It has the capacity to shift from one stable state to another stable state. It can toggle between two equilibrium states. So this is the meaning of a bistable mechanism. Now, I also use the word compliant mechanism. Now, what are these? These are flexible mechanisms which transfer the input force and displacement at one port to an output force and displacement at another port through elastic body deformation. So these are basically jointless structures or single piece structures. As you can see here, there is no joint out here. There is no joint here. This is just a single piece structure. So when you have the single piece structure through basically elastic body deformation, this is an elastic, when you apply a force by elastic body deformation, it is moving without the application, by the application of a force. It is able to toggle between two equilibrium states and it is able to stay there. Right? So this is what is known as a compliant mechanism. Now the question is, how can this mechanism that you just saw here be used for gripping? This is what we explored. Right? So this is the gripper that we built. This is the beam, the bistable buckled beam. This is the beam that you have here. These are rubber pads which are attached, and these are two plates which are connected by uh, rods which are bolted to both of these plates. Now this is the structure of the gripper. Now you can see here that, let us say that the pole is between, right here, between these two sets of rods and these two sets of rods. Let us say you apply a force in this area out here, right at the center over here. Then of course this will move into this particular bistable buckled beam. This will press this rubber pad forward, right? So that is one equilibrium state. And when a force is applied backward, then of course it comes back. Just to explain this in more detail, let us just consider the top view, right? This is the top view. This is the pipe that you have here. And this is the gripper which I just showed. Now this is the pre-stress bistable buckled beam in the off position. This is the rubber pad that you have here, right? So this is one configuration. It is a stable configuration. Now when you apply this transverse force, this, as you can see in the second figure, is moving to its second position, second stable position, and it is pushing this rubber pad onto this pipe, onto the wall of this pipe, thereby enabling it to grip the pipe. So these two positions that you can see here, this position here and this position here, these are the two stable positions. So this is similar to what I just showed in this video. So just like you have one stable position, and when you press it upward, you get the second stable position. So the same way, You have one stable position, and when you apply this transverse load, it presses this rubber pad onto the pipe, thereby enabling it to grip the pipe. So this is how we had. This is the basic idea behind using this concept of bistable compliant mechanisms to actually provide force to press this rubber pad onto the pipe and hold on to the pipe. So this, I won't go into much of technical detail here, uh, but I'll just briefly explain what we had done. The design of this gripping mechanism basically it involves the selection of the dimensions of the beam, because the dimensions, the thickness, for instance, how much we are, the distance by which we are deflecting it initially to create the pre-stress. That, of course, is dependent. It is related to the gripping force, how much force it can actually provide to be able to grip this particular pipe, right? So what we had to determine, was basically how much force to basically apply to this particular beam in this configuration to snap and move to the other configuration so as to grip this pipe. So that is what we basically called as the snapping load, right? Now, how did we um, find out what is the snapping load? So here we created an experimental setup, right? You can see here, this is the beam. This is one configuration of this beam. It is clamped at both ends, right? Um, Now we attached a load onto this beam, a transverse load onto this particular beam, and we slowly went on increasing the weight until it snapped and moved into the other configuration. So this is one configuration that you can see here. This is the second configuration. And based on that, we got an idea of how much force is needed to make it move from one configuration to another configuration. This is how we did the test. Regarding the actuators, we actually actuated these grippers using a cam-driven system. So I hope all of you are familiar with what cams are. They are basically used for, um, depending on the cam profile, you can get a particular type of uh, uh, driven motion. The cam, depending on how you build the cam profile, at particular points, it can actuate this uh, bistable buckle beam and create the force which is necessary for pushing this bistable buckle beam onto the opposite direction into the other configuration. So here you have a motor which is running, and this is rotating um, this cam, right? It is driving this cam. Now, depending on the cam profile, on what kind of profile you have for this cam, it will hit this bistable buckle beam at a particular point in time, and accordingly it will be able to uh, push it to the other configuration. I'll just show a video of this. So here you have the cam rotating, right? So this is basically pushing it. You can see this is the beam here. It is now in one stable configuration. Then this cam basically comes in, and this cam pushes it downward into the other configuration. And this first cam again rotates depending on the profile. It again is able to bring this back to its original first configuration. So one cam will make it go from one configuration to the other. The second cam is basically a retraction mechanism. It brings it back to the first configuration. Um, so we developed this pipe climber in this manner. This is the a structure of the pipe climber. We divided the pipe climber into two portions, the upper portion and the lower portion. As I mentioned, in an inchworm climber, The basic idea is that the body has to be divided into two portions, upper and lower. First, you fix the lower one, you move the upper portion forward, then you clamp that, and then you move the lower portion upward. So these are some snapshots. So here you have the bottommost position. First, the top portion moves upward with the lower portion fixed. Then the top portion is fixed and the lower portion is moved upward, and so on. So slowly you can have a movement of the robot upward. I'll just show the working of this. So here you have the cams operating to first lock or unlock this particular lower portion. And once it is unlocked, then this top portion moves upward due to this lead screw that you have. You can see here, this is a lead screw that enables the top portion to move upward. Then this top portion is fixed, and this bottom portion moves upward. I don't know, maybe there's something wrong with the video. It's playing very slow. Uh, this, yeah, so this is the robot basically moving upward. Right, you can see this is moving upward. There appears to be some problem with the video. It's playing pretty slow. Right, so this one will now be clamped, and the lower portion will now be unlocked. Now the cams will unlock this particular gripper, and this lead screw will now enable this bottom portion to move upward. So this cams basically play the job of actuating this particular gripper at the lower and the top portion. They unlock, and one cam locks the gripper, the other cam unlocks the gripper, and the lead screw is what enables the upward and downward motion of both of these components of the robot, the upper portion and the lower portion. So this was the end of my presentation. Before that, I just want to share I think there was something wrong with that video. Um, could I just share, Dr. Shivraman and Dr. Vasu, could I just share the video separately?
Yeah, no problem. No issues. Sandeep.
Yeah.
No issues.
So I hope you can all see this.
Now it is clear, sir. Now it is clear. Perfect.
Yes. So I'll just go back to this. So this one was the video of the cam, how one cam is actually shifting it from one equilibrium state to another. You can see here, it is pressing it downward, right? It's pressing it downward, and this second cam is actually bringing it back upward, right? So one is locking, the other is unlocking, right? So this is the gripper, how it operates. So first, the lower part is locked, right? And the upper portion is moved upward. And then the same process is repeated for the lower part. So here it is moving upward now, right? Now the cam here locks it. Now this one unlocks it. And now this lower portion is now moved upward. So the cam is basically playing the role of locking and unlocking, and this lead screw is what is making it move upward and downward. Right. So I think that was uh, yeah. So that was the end of my presentation. Um, if any queries, you can please ask me. I'll be willing to.
Yeah, you can see in the chat box one question is there.
What is the suitable criteria for choosing the right kind of motors and actuators to design a pipe climbing robot? Please discuss some examples. The right kind of motors, these were actuated using servo motors. Motors and actuators. Uh, I think these were motors are of course used to actuate only. The motors which I used was servo motors. Um, these are basic. I mean, what criteria means? There are, I mean, of course, many advantages. AC motors, they're different kind of motors. Um, one criteria which is often used is the ease of controlling the motor. You must be able to control it easily. Um, it need not be the case with all motors, and it also depends on what you're trying to actuate. Here you're trying to control the cam profile. So if you saw what I was trying to do. Sorry, what is that? What is the controller used for controlling?
Yes, sir. Hello.
Yeah. If
Yeah,
you could
sir.
please
Good
clarify your
afternoon,
question.
sir. Good morning, sir. Actually, uh, clarification is that like for controlling the motor, what type of controller you have used? Maybe have you used any kind of feedback controller or something like that?
Oh no, this was controlled simply by using Arduino boards.
Adreno controller, it's
Yes,
microcontroller
yes.
by simply using microcontroller.
Yes.
But sir, how this gripping mechanism and how will compensate with that gripping mechanism and the weight of the robot? So how that heavyweight robot will be move or climb? How will take care of the gravity? How will take care of all this gripping?
This we had actually calculated the weight of the robot, and we had all these cams, the design of them, the dimensions of them. They were actually designed keeping in view the weight of the robot. So we did a proper weight analysis. When we if you see my presentation,
Yes, sir.
I'll just go back to my presentation. Yeah. Yeah. So here you can see, right? So here, when deciding how much of force to make it grip and so on, right? So this we had
Yes,
done a proper force calculation for how much force is necessary to push it against the um, to push it against the pipe. So when we were doing these experiments, actually we took into account the fact that the weight of the robot is some X number of kilogram, and we factored this into this weight. So even though this may have shown that, for instance, this weight was sufficient to make it go from one configuration to other, we ensured that some sufficient additional weight was added uh, to ensure that it is able to grip the pipe, keeping into account all the entire weight of the robot also. So it wasn't just this weight. We added some additional weight, keeping into account what all components are there and how much they weigh also. So that is why
sir.
when this beam was actuated and this pushed on to grip the pipe. So the weight that we gave was a bit more than this weight here.
Okay. Sir, it's depend upon the material also, na? Which material you have used to design that one also.
Yes, yes. So this cams, okay, maybe I forgot to mention, these cams, they are made of mild steel, and they've been
Okay.
fabricated using wire cut EDM. Um,
Okay.
the cam shaft also we have made from mild steel.
Okay. Okay, sir.
So this we have used mild steel for this. So this we actually built the cam profile. We designed the cam profile from scratch.
Okay.
I have not presented the details here, but we did it from scratch.
And sir, what about that? You have discussed about the inchworm climbing and all that. So whether the climbing mechanism and your down mechanism both are same, or is there any other mechanism to uh, because after completing the job, it should take less time to come down or something like that. Is there any other
Uh,
mechanism for that?
No, in this case, the upward climbing and downward climbing is the same thing, because these cams basically they are timers. If you see at a precise timing, the rotation will ensure that at a precise time, this will be
Yes,
snapped
yes.
downward, and this one will go down and push it down. So all these happen at precise timed moments. So cams, as you must be knowing, they are used in switches. They are used as timers. So if it is happening at precise times, then it means that upward climbing and downward climbing, there is no difference. It is just happening at different times. That's all.
Okay, sir. Thank you, sir.
Yeah. Any other query?
Participants, you can unmute your mic and you can able to ask the expert if you have any queries. So for the queries, sir, Sandeep, just I have one small query. What are the challenges if you want to design any particular robot for the internal pipe climbing? So what are the main challenges? Just I want to ask.
Internal pipe climbing is difficult in that developing navigation and control is difficult, and um, especially when you are dealing with pipes of changing diameters. That is especially difficult because it means that when you are going through the basic idea behind gripping is that when you are climbing a pipe of a particular diameter, then the robot has to be such that its entire length must be such that it must cover the whole diameter of the pipe. Now, suppose the diameter changes, then the robot basically has to shrink. It has to find a way to uh, close down together and then enter that smaller diameter area, and then again it has to if the diameter changes again it has to adjust. So this designing these kind of things are difficult. That is the first challenge, and second, this I can mention from personal experience also. We were interacting with oil company people, and they said that one of the things that they would like is that if we could build a robot which to pure mechanical components, because what you have in a lot of these oil pipes and nuclear industries, nuclear pipelines, there is an apprehension that if you use some kind of electrical equipment, it may create some kind of sparks or something like that. So, from personal interactions, when we interacted with people from the oil industry, they said that they would be looking future they would be looking to looking for robots that are built through pure mechanical means, to without any electronic, without much of electronics. So that is another challenge. I mean, how do you do this purely mechanically? So it's interesting problem.
Yeah. So nice, Sandeep. Yeah, participants, if you have any other questions, last question, so we can able to ask any other questions. We can expect one last question.
Sir, I
Yeah.
have another question, sir. Because just now, sir told about that it is purely mechanical. But because you need at least that controller and all these things, so electronics part must be there.
Uh, you're right. You're right. That is why I said it's a challenge. I mean, I don't have an answer to that. That how you're going to do it. But I mean, see, that is the problem in the oil industry. People, they are apprehensive. They are very apprehensive that especially in nuclear power plants, that they say that we.
See, sir, if we go for like pneumatics and all that things, maybe we can reduce.
That only just pneumatic, and you can go for DC synchronous motors like that, where we cannot have any contacts will not be there. Like that, we have to go further. Yeah.
Yes, sir. Yes, sir.
So,
That could be a possible
yeah.
solution. It has to be
Yes.
explored.
Yeah. Yeah. Okay. Then
Thank you, sir.
if you
Thank
have
you, sir.
no other questions, then we will thank the expert, Dr. Sandeep from IIT Guwahati, for giving good insight on what are the climbing robots, and this is going to be one of the best area, as the Sandeep has mentioned. So this ONJC and this Gale, these are all looking for this type of challenge robots for internal inspection. So in our every year we used to have one big explosion of either this pipeline leakages in this particular ONJC and Gale and these Reliance people. So they are having this. They want this particular inspection robot for their particular pipeline, because it is not at all possible by human, because the pipelines are going to be underneath the ground, and some pipelines will be underneath the sea. Okay, that is going to be one big challenge, and they are going to be having a lot of scope in that research area, and the people who are want to take some topic on that, that is going to be one challenging area they can able to take in that particular area. So I once again thank the Sandeep for his nice innovative session, and his thank you once again for bearing us his valuable time to share his knowledge in this particular FDP workshop. Okay, so thank you, Sandeep.
Yes, thank you, thank you. I can log off.
Yeah, you can log off, sir. Okay. Yeah.
Thank you.
So the participants, we will have a break for 20 minutes, and we will come back by 11 o'clock. We will have the session 2 from the Patel, Naveen Patel from IIT Madras. He is able to give you another important, nice, challenging research topics, where you can able to have the medical robots and the surgical robots. This is also one of the biggest area, if the people who want to do some research on that, and that is going to be one of the biggest area. You please on time, so we will be start the next session by 11 o'clock. Okay.
Sir, this is Upendra. Actually, the feedback form is shared, so I request all the participants to fill it. It is shared on the WebEx chat box as well as WhatsApp group also. Thank you.
Thing is, today afternoon, once again, just I have already messaged you. Today afternoon, we are going to be having one assessment exam will be there for 20 questions will be given for 20 marks, and half an hour time, and you will be shared with the Google form. Once again, you have to fill that one. That is going to be mandatory as per the ACT. And now I will request you to all of you, invite you for the valedictory function at 4 o'clock. And in this, our one the chief guest is going to be our director of NIT Warangal, Professor Ranveer Ravanrao sir is going to be the chief guest for that. So you don't miss these two things because to complete this function or this is going to be the mandatory things which are going to be required for that one. Okay. So with this, you take 20 minutes break. We will meet at 11 o'clock.